linear chromatography, TLC, is a method used for rapid qualitative analysis, where components in a mixture can be separated and identified. This video is focused on the general method or procedures used in TLC, and for information on the theory, you can check out your lab manual or lab guide. Separation occurs on a thin layer of silica on top of a solid support such as a sheet of glass or a sheet of plastic as seen here, and this is called the TLC plate. The properties of the silica and the properties of a solvent are used to draw the components up the plate. Differences in the properties of the components in the mixture mean that each component will travel up the plate at a different rate, and this causes a separation. The separated components can be identified by comparing how far they travel along the plate relative to reference material, also known as standards. Let's take a closer look. First of all, we need to prepare the TLC plate. Make sure that you handle it only by its edges or use tweezers since we don't want to contaminate the silica gel surface. A ruler is used to draw a line using a pencil about 1 centimeter from the bottom edge of the plate. And draw only a very light line and try not to score the surface of the silica. This line is called the origin. Vertical markers are spaced about 1 centimeter apart along the origin. These markers are used as points of reference when applying mixtures and standards dissolved in a suitable solvent. And here we are going to run 4 lanes, lane A, B, C and D. In this demonstration, we're going to see how to separate and identify using TLC. In this bottle, the identity of the contents is unknown, but we do know that it contains either compound X or compound Y, or even a mixture of both. In this bottle, we have an authentic sample of compound X, a sample which we know beyond any doubt is compound X, so we call it standard X. This is our first reference. In this bottle, we have an authentic sample of compound Y, sample which we know beyond any doubt is compound Y, so we call it standard Y, and this is our second reference. The first part of the TLC analysis is to spot the plate. We use a capillary applicator to apply a spot of standard X at the origin in lane A, and again in lane C. Now in lane B at the origin, we apply a spot of standard Y, and once more at the origin in lane C. And note how we use a clean capillary applicator with each solution. This is to avoid cross-contamination between the lanes. And so with a clean capillary applicator, we apply a spot of the unknown in lane D. So looking at the spotted plate, we have standard X in lane A, standard Y in lane B. In lane C, we have a mixture of standards X and Y. And in lane D, we have our unknown, which is either X or Y, or a mixture of both. Let's find out the composition of the unknown. A pre-measured volume of a suitable solvent is added to the developing chamber. You'll normally be told which solvent to use. The developing chamber is covered with a lid for a few minutes, and this few-minute waiting period allows the atmosphere inside the tank to become saturated with the solvent vapours. The spotted plate is quickly placed inside the developing tank so that the bottom end is immersed in the solvent pool. We must always make sure that when we first put the spotted plate into the solvent pool, the origin is above the surface of the solvent. Generally, the solvent will take just a few minutes to ascend the plate, and we can usually see the front edge of the now wet silica slowly ascend the plate. This boundary between dry and wet silica is called the solvent front. When the solvent front is close to the top of the plate, say about 1 centimeter from the top, the plate is removed from the developing tank. and the solvent front is quickly marked with a pencil. There are a number of ways to see, or as we say, visualize developed TLC plates. A common method is to place the developed plate underneath an ultraviolet or UV light source. This method of visualization is by far the most common in your lab. If a fluorescent indicator is added to the silica will fluoresce under UV light. Chemicals on that plate, however, will usually show up as dark spots. Sometimes, when the chemical on the plate is UV active, the spot will fluoresce a different colour than the silica and be visible in that way. But most compounds will just show up as dark spots against the fluorescent silica background. So while visualizing the plate under UV, we're now able to outline all the spots with a pencil so that we can locate the spots under visible light. And once all the spots are outlined, we can remove the plate from the UV light box. And now that the plate is no longer under UV light, we can see all the spots together with the solvent front. Let's take a closer look at the results. By comparing the results in lanes A and B, we can see that compound Y has travelled further than compound X. Now comparing lane C with lanes A and B, we can conclude that the lower spot is X and the higher spot is Y. This is called indexing the references. Finally, we can now compare the unknown in lane D with the standards or references in lane C. This allows us to identify the unknown. Although it's pretty clear from this result that the unknown was actually compound X, we can also characterize spots on developed TLC plates by their RF value. The RF value for any spot is equal to the distance moved by that spot in millimeters divided by the distance moved by the solvent, also in millimeters. Now, using this developed plate as an example, and assuming that RF values for the spots 1 and 2 in lane C have already been determined, let's now obtain the RF for the single spot in lane D. The distance moved by the spot from the origin to its centre is 28.0 millimeters, and the distance moved by the solvent from the origin through the spot to the solvent front is 80.0 millimeters. The RF for this spot is thus calculated to be 0.35. Note that it's customary to report RF values to 2 decimal places. In this example, the RF of 0.35 for the single spot in lane D compares favourably to the RF of standard X in lane C, so we can confirm that the unknown was in fact compound X. Here we see the measurements being made and recorded in the notebook. RF values calculated and also recorded. The closer the RF value of an unknown is to the RF value of a standard, the greater the chance that the unknown is the same as the standard. This is what allows us to identify unknowns in mixtures by comparing RF values of the unknowns with those of standards. It's unlikely that RF values of analytes will exactly match those of the standards to the second decimal place. This is due to a combination of experimental error arising from various factors, including measurement uncertainties and inconsistencies in the TLC plate. Nevertheless, in most cases, it's possible to confirm the presence or absence of a compound by comparing its RF value to that of a reference or standard run alongside it on the same TLC plate. Here we can see that the RF of the spot in lane D is much closer to the RF of compound X than the RF of compound Y, and since we knew that the unknown was one or the other, we can confirm the unknown's identity as being compound X. This completes this video on the TLC method. You can check out more of our instructional videos on our YouTube channel at Capilano U Chem Lab, or for a full catalogue of our videos, check out our website at capuchem.ca/labs. Thank you for watching.